Today, we're digging into alkyl halides and what gives them their unique chemical personalities.
It all boils down to one single incredibly powerful bond inside these molecules. Let's check it out.
So what are they? Just a basic hydrocarbon that swapped a hydrogen for a halogen partner. Simple as that.
Now this bond is polar. That's because halogens pull on electrons way harder than carbon does.
This little tug-of-war creates a charge difference, making the molecule act like a tiny magnet.
And that stickiness comes from two main things: dipole-dipole interactions and van der Waals forces. It makes sense, right? The stickier the molecules, the more energy it takes to boil them.
And you can see it here. Boiling points shoot way up as we go down the halogen group.
This chart really drives that point home. But you have to ask, why does this happen? It all comes down to those van der Waals forces. Bigger halogens just have a stronger grip.
Of course, the molecule's overall size and shape play a huge part in this too.
So, what happens when we try to mix these things with the most common liquid on Earth?
Well, the heavier ones, with bromine or iodine, are actually dense enough to sink in water.
But here's the weird part. They're polar, so shouldn't they dissolve? What's going on here?
Long story short, water's own bonds are just too strong to bother breaking up for these guys.
Okay, so which bond has the biggest dipole? You'd think carbon-fluorine for sure, but there's a twist.
Look at that. It's actually the carbon-chlorine bond that has the highest dipole, not carbon-fluorine. Surprising.
So why is that? Well, fluorine has more charge. The CCl bond is just significantly longer.
So, here's the big takeaway. That one single polar CX bond dictates almost everything.
Their boiling points, their density, why they don't dissolve. It all traces right back to that one bond.
It just goes to show how tiny changes at the atomic level can lead to massive differences we see.